Hey everyone, I'm going to take a look at some frictional problems. We're working on friction in physics, and there are a lot of different scenarios that you can come across. So what we're going to do is take a look at Unit 5, Worksheet 5, problem number 4. It's the one on the back with the skier. I'm going to walk you through the problem, and tomorrow when we take a look in class, we'll be finishing up a couple of challenge labs, and this will be your resource for these kind of problems. We've been working with forces, so all of the same setups apply. We want our free body diagram. We're going to get our net force and our max and May equations. So we're going to get everything in place and come up with a solvable equation to figure out the acceleration of this guy. He's a skier on a slope. So I'm going to bring up the problem here. All right. And on the worksheet, there are a couple of questions that go along with it. We're just going to do the whole problem, and in doing the problem, we'll be able to answer those questions. So here we go. We have a 84 kilogram skier glides down a hill with a kinetic coefficient of friction of 0.5. I'm just going to make sure my pen is live, and I like all my stuff. There we go. So first thing, free body diagram. So here's my skier. He is on Earth. I've understood why. Okay, so here's my skier. He is on Earth. I have weight down. He's on a surface. It's going to do normal up. I know that he has some friction in the problem because it's telling me there's a coefficient of friction. So if there's a coefficient of friction, there has to be friction. It's going to oppose the motion. So the skier is going down this slope. I know that it's going to be opposite that motion. And so there's my friction. A lot of times folks have the tendency to want to draw a force on on this plane down here. And that's not the case because, and you know, it's so funny, you probably can't see what I'm drawing. I feel like you can't. Yeah, you can see what I'm drawing. It's just not on my screen. Sorry. Totally awkward. I know that the skier is going to go down the hill because of the weight in the X plane, right? That's what's causing him to go down the hill. He's not going down the hill because there's some forward force. You only draw forces that are there. That's all that's there. Once you have your forces drawn, you can break up any force that doesn't lie in the XY plane into its components to see where that is. So let's get an XY plane in here. All right, so I'm going to have my Y plane right along here. And then the X plane is always going to go down. Okay, so this weight vector does not lie on the XY plane. So I'm going to go ahead and break up weight into a Y component. So that's my weight in the Y weight. Sorry. And then this is my weight in the X. And then I can see that weight in the X, in order for him to go down the hill, it's got to be larger than his friction, or he's not going anywhere. This angle theta down here is this angle here, so I'm going to bring my weight in the X, right, like so. Make my right triangle. There we go. So now I've got my free body diagram done. I've got all my forces. I've resolved them into the XY plane. Next step is to go ahead and get my statement of net force. F net is equal to MA. In the bottom of the paper, you can't see here on the screen, but it's asking for the acceleration of it. But he's going down a slope. I'm going to assume he's accelerating. It doesn't say that he's moving with constant speed, so we're going to assume that he's accelerating, but the problem asks for acceleration. So I'm going to leave that there. I'm going to sum up all my forces, and I'm going to come down underneath of here just so I have more space. I'm going to sum up all the forces in the X. And I'm going to choose down to be positive just to make my life easier. So weight in the X minus friction. And then sum of all the forces in the Y direction is going to be normal minus weight in the Y. I'm accelerating on this plane. He's not bunny hopping or doing moguls or anything like that. So only in the x-plane am I accelerating. So ma is equal to, these guys here, I know they break out into larger or more, they break out into different equations. Not larger equations. I guess you could call them larger, but they are written in more fundamental terms. W and friction are not fundamental because they're not either given or known in the problem. So I want to get them into more fundamental terms. So weight in the x, weight is mg, and then the x component of weight. So since this is my trig setup, it's opposite the angle. So it's going to be mg sine theta. And then friction, I know from, the mu the shoe lab and from my equation sheet, I know that friction is equal to mu, and it's kinetic. So mu, the coefficient of kinetic friction for this problem, times the normal. Normal is not a fundamental term, but I can get it into a more proper term. So this, in the y-plane, we're not moving up or down in the y-plane. So normal is equal to mg cosine theta, right? The y is on the adjacent side of my angle, so that is cosine theta. I can solve this out. mg cosine theta is equal to normal. That allows me to take this and plug it into here. I'm just coming over a little bit to give myself some more space. MA is equal to mg sine theta minus mu sub k mg cosine theta. I'm asked to find the acceleration. You're also asked to find the force of friction. So you can go ahead and solve this equation here to get the value for friction. And then you can go ahead and, come back to this equation. We're going to solve this for A. So we're going to get A is equal to, so this is the mass of the guy. This is the mass of the guy. This is G. So I can pull out mg. Sine theta minus mu sub k cosine theta. And when I divide out the, the m here, I've got myself an equation solved for A. So go ahead and sub in and solve. I'm going to do the same thing on my calculator real quick. Again, we're live, so if this is a video, obviously you can fast forward, but if we're live, you've got to hang in with me. So I'm going to go ahead and do my sine 20. And mu is 0.15 times the cosine of the angle, which is 20. Times. It's like they say in the radio, never have like silent air. I should be playing some like music in the background. Okay, so 84 times 9.8. So I got 164 meters per second squared. Totally not the right answer. So let's take a look at this real quick to see what where we're going wrong. So 84 kilograms times 9.8 meters per second squared times sine of 20, sine of 20 minus 0.15 times cosine 20. Oh, probably forgot to divide out the math. That would help. Divided by 84 kilograms. I could probably fit that in. Yes, I can. Okay, so let's try that again. That's a 20 over here. All right, so cosine 20, 0.93 times 0.15. Awesome. So that's 0.2. So this is 0.2. So 84 times 9.8 times 0.2 divided by 84. 1.96. That's more like it. Awesome. So we get A equaling 1.96 meters per second squared. Sweet. Good deal. So a couple of things to recap, and then I'll let you loose. Remember, always free body diagram first. Break up your forces, resolve all your forces into the XY plane. Remember, this guy's going down the hill because he's on a hill. Gravity's going to act on him, but it's only his X component of motion, meaning that's all that needs to overcome that friction. It's heading down the slope. In order for me to solve for acceleration, I need to get a term, equations into the right terms. So I went ahead and did that there. This does become a pretty big equation, but all you're really doing is getting a solvable equation all in one step. You could go back in and solve for pieces and put the numbers together, but ultimately this is really what we're after here. Right? Is that equation A is equal to mg times the product of sine theta minus mu cosine theta all over m. All right, cool, sweet. I'll let you guys loose. Thanks for watching, and I'll see you next time. We're working on more force problems when we come back, and look for other archive videos going back to kinematics, projectile motion, and force problems not involving friction or inclined planes. This is involving friction and inclined planes, so obviously a little bit more involved, but we have some other videos you can always go back to. Cool, thanks for watching. Subscribe, and I'll see you next time. Now for the awkward pause.